Welcome to part 3 of Lecture Online. We are going to go deeper into polar graphs and find the workings of how polar is graphed. Now, let's start with what we're familiar with. And by the way, this is going to be in radians. Okay. Now, we are familiar with the unit circle, which of course starts with 0 and has some angles here of, let's write these ones, of pi over 6, pi over 4, pi over 3, pi over 2, and so on, going to pi, 3 pi over 2, and back to 0, but since we're rotating, it's 2 pi. Now, one concept in polar graphs that's extremely important is rotation. Because unlike the rectangular coordinates that we are very familiar with, finding a point and simply looking at where it's located, 3 to the right and 4 upwards, instead of simply looking left, right, up, and down on where a point is, polar in radians has rotation. And what that means is basically if we were to find a point at, let's say here, which would be labeled as r comma pi over 4, we would know where that point is because pi over 4, the angle, r comma theta, the angle is pi over 4, meaning that we start from the bottom at 0 degrees, or 0 radians, and we rotate upwards to pi over 4 and find the radius between the origin and the point. And now we know where our point is located, again, from pi over 4 telling us that you rotate upwards pi over 4 radians. Now, let's take a much larger polar graph and sketch. Now, once again, unlike the rectangular coordinate system, polar has the radius and the theta, the angle which you rotate. Now, polar graphs are graphed in terms of the radius, so we're going to draw circles around here since we're rotating, and the circles will tell us the location of our point in terms of the radius. For example, this first circle is going to be radius 1, and the second circle is going to be radius 2 and radius 3, and so on. Now, if we draw the same angles of pi over 6, pi over 4, pi over 3, or 2, oops, forgot 0, 0 pi, 3 pi over 2, and 2 pi. Now, if we have this here and we decided to graph the point, again, pi over 4, but at radius 2, we would label this as 2 comma pi over 4. Now, once again, rotation is extremely important in polar graphing because there are an infinite amount of ways to graph this point right here. For example, I can go to radius 2 down here and go upwards pi over 4 radians, and I know where my point is, going from the radius 2 and then pi over 4. Now I can also graph this as 2 comma pi over 4 plus 2 pi. And because I'm rotating, it would be the exact same point because I would go to 2 and my radius, so 1, 2, and then I would rotate 2 pi radians, which means going a full circle here, and then rotate pi over 4 upwards. And you get the exact same point. Now I can also write this as 2 comma pi over 4 plus 4 pi. Because once again, we will start with radius of 2, rotate 2 pi all the way around, rotate to 4 pi all the way around once again, and then rotate upwards pi over 4, giving us the exact same point. And now, getting a bit more complex, but using the same concept of rotation and being able to graph this in infinite amount of ways, we can also graph this as negative 2, a radius of negative 2, comma, pi over 4 plus pi. Now, we start at negative 2, and then we rotate pi radians over here, and then we rotate pi over 4 radians back to the same exact point. Now, the concept of rotation is extremely important for graphing polar graphs and is very important for domain because, I'll show you over here. With the domain, it would be, we wouldn't want to write a polar function with the domain of infinity every single time because we can graph it in infinite amount of ways because it keeps on rotating infinitely. So we need to know the concept of rotation to see when the graph comes back to the point where it began so that we know where it started and ended. So for example, let's take another graph. And we will graph here a simple function of r of theta equaling sine of theta. Now, let's make a table of values to see how this happens. So, let's make since our amplitude here is 1, and knowing, remember from previous courses that the amplitude is simply the height at which the function, or the height of the trig function, that we're going from sine starting here on a rectangular coordinate system. Sine would start here at the origin and then come up to 1 and then come back down to 0 and then come down to negative 1 and then back up. And at these points it would hit 1 at pi over 2, it would hit 0 at pi, it would hit negative 1 at 3 pi over 2 and go back to 0 at 2 pi radians. Now, in rotation, in polar graphing, it's much different because rectangular, it goes on to infinity because this graph oscillates. It does, I wouldn't say it rotates, it oscillates. But in polar graphs, the sine function or any r function will rotate. For example, let's make a table. So theta of 0, you'll get an r of 0. And then going to, we'll keep it simple. Let's just go like we did before over here. Pi over 2, we'll get 1. If we get to do pi, then we'll get 0. 3 pi over 2, we'll get negative 1. And 2 pi, we'll get 0. Now what does this look like on a graph? On a polar graph, this whole graph will be a radius 1. We start at 0 here, and we'll rotate pi over 2, and, excuse me. We'll actually need an angle in the middle. This we will put pi over 4, which is approximately 7. Or excuse me, not 7.7. Excuse me. So we start at 0, and at pi over 4, we rotate from 0 to approximately 0.7. So we will rotate here. And then at pi over 2, the angle pi over 2, we'll rotate to 1 up here. So it'll rotate here. And then, again, because of symmetry, this will rotate down here. And at the angle of pi, we will come back to 0. Now the graph is already completed from 0 to pi. So like I was saying before, rotation is extremely important for domain because this graph's domain would be from 0 to pi rather than saying from 0 to infinity, because there are an infinite amount of way, or because this graph does technically rotate infinitely because it just overlaps the previous rotations. So now we know that this graph, that the graph r theta equals sine theta will have the domain of from 0 to pi because of the polar graph's rotation.